We're going to talk about fourth order Runge-Kutta. Okay, and first of all, Euler and Hoynes methods, they come from a class called these Runge-Kutta methods. All right, these are both kind of single point methods because we find this next value based upon the current value. There's also these multi-point methods, and they actually look at, the current value, maybe one behind, maybe two behind, so on and so forth. And we have another slide in a couple of minutes about multi-point methods. But effectively, all the fourth order Runge-Kutta are all based kind of on this single point method. Okay, and the most popular of the Runge-Kutta methods, right, is kind of this RK4 that we're going to talk about. But I want to talk a little bit about kind of this fourth order process. Okay, now Euler, I haven't mentioned it yet, but it's first order. Okay, in the sense that the first two terms, if you recall, first two terms of Taylor series were kind of used. Okay, and Hoynes method is a little bit more information about that. We're kind of using kind of a slope of those. Okay, so it's not quite the first two terms, but it is kind of a second order model because we're using more information to try to get a better approximation of the slope. Well, there's third order models, okay, and then of course you can go all the way up to, well, fourth or even higher, fourth order, okay. And on the next slide is an example of just one of those. Let's go, and my mouse is over here. All right, so what is it? Well, we have this first order model thing going on right here. We saw that with the Euler step. And then we kind of saw something similar to this right here with Hoynes method. Okay, we didn't quite do the exact same sort of thing. All right, we'll talk about her in a second. But with a fourth order model, well, we're going to kind of keep on doing this process until we get down to, well, a specialized Euler step where we have a really good approximation for what that slope should be based upon a whole bunch of previous stuff beforehand. We're going to call them K1, K2, K3, and K4. But they are very similar to just a whole bunch of slopes, okay, because these functions are all just slopes, calling them at different times. Okay, you can notice then that it's kind of weighted interestingly, where somewhere in the middle, okay, we can see that similar to Simpson's 1/3 rule and Simpson's 3/8 rule, we have kind of a scaling factor. That's of course because there's 1, 2, 3, 4, 5, 6 of those. We want to kind of have an average slope of those, okay. And the benefit of an RK4 method or Runge-Kutta is that the global error is going to be, well, 4, okay, which means effectively that if you think about the order, okay, of these methods, it's not necessarily related to Taylor series. It's really related to kind of the order that we'd expect within the error in terms of global. Okay, so if you recall, we had Euler's method globally. It was on the order of delta t. Okay, Hoynes method was on the order of delta t squared. And then we're going to call what's Runge-Kutta 4. Maybe I'll just fix that up here a little bit. Runge-Kutta 4. Okay, is going to be on the order of delta t to the fourth, and this is all for the global error. Each one of these one steps would be increasing it by 1. So the local step for Euler's method would be delta t squared. The local step for Hoynes would be delta t to the 3. And the local step for an RK4 method would be delta t to the 5th. All right, so let's kind of walk through this a little bit. On the previous slide I introduced these, but now let's kind of talk about how we're doing an average of all these slopes. Well, the first one right here, okay, is this guy right here, okay, where we're doing nothing more than trying to take the slope at this particular point, and that slope value is going to be called K1. We march forward in time, okay, but we march forward in time only I plus 1/2. Okay, we really want to go from here to here for the full time segment, but we're going to go half that time and then take a look at that next value right there and then make a function call to figure out, well, the slope of that next point right there. That's going to be K2. Okay, so we go forward in time by 1/2 delta t. Okay, and then we're going to take a look at, well, kind of like that predicted slope, but in this particular case, it's going to be the prediction of y. Okay, taking K1, scaling it by 2, okay, and then marching forward in time using that value to then extract out K2. All right, well now we use K2 in the next equation right here to figure out the next one. Okay, so we go and take K2, which is this angle right here, back to this point, and then march forward in time along K2 to get, well, K3. Then we go back and march along K3, but now this time we're going to march all the way, okay, that's why this is all the way, okay, to get K4, all right, and then finally we go back here and we take K4, we take K3, we take K2, we take K1, and we average them all together to get, well, this vector right here. And then finally we march forward in time, okay, this last step right here, to actually get the real value that we want for y1. So if this was y0, okay, this would be the next time step of y1, assuming that I is equal to 0. All right, so I'm going to go off and I'm going to add another method, okay, to this file that we've been talking about in MATLAB. All right, I'm not going to talk too much, all right, because you'll just be able to see, hopefully on the left-hand side, what I'm doing to kind of change this. But then at the end of the day, we're going to compare these different methods, and I might even speed up the video at this time. Okay, so I'm back, all right, um, and hopefully you watched a little bit about what I was typing, and maybe you kind of saw, some mistakes or things that I could do to improve, that sort of thing. But essentially what I'm doing then is that I figured out that first K1, and then I use that K1 to go forward in time a little bit to get the next Y value. Okay, so this is nothing more than kind of like an Euler step, but I'm going half in time along that slope right there to get my next Y value, and that's going to be placed into my function to extract K2. From K2 I get K3, from K3 I get K4, and then I do an average of all of those slopes, and then I finally move forward in time, moving from Y to my next Y, I plus 1, but of course with R standing for RK4 method right there. All right, I'm going to save this as a different function. It looks like I misspelled Hoynes, so I need to go in there and, oops, put a U in there. Our Euler, Hoynes, and RK4 method. Okay, I'm going to save that right there. I'll try to post this to Learning Suite here in a little bit. Okay, I've set my DTH for Hoynes method and DTR 0.5, and also Euler's method, which I maybe should have put an E there, but it's kind of the basic one right there. And now I'm going to see if I'm close. So I'm going to hit Control S, I'm going to run, and we'll see if I've got an error-free example for you. Let's see, I don't have an error-free example because I wanted to go up and do this first example first. So let's do that one. Let's do that one right there. Okay, and since I'm doing example number 1, I probably need to set this going up from 0 to 1. Oh, and if I remember, I like to have this on the northeast for example number 1. Okay, so let me bring in the figure from my other screen, and then you can kind of compare again this Euler method, all dt's at 0.5 to Hoynes in the RK4 method. All right, so Euler's method, of course, was under-predicting. We knew that Hoynes' method was over-predicting, and let's see how the RK4 method does. Okay, fourth order approximation. All right, so far it's really good. Let's keep on zooming in to this one point. Looks like it's almost hitting it dead on. Okay, so we're gonna get rid of Euler's, just focus on Hoynes and RK4. Okay, so far it's still really good. Now we're going to focus on just this one RK4 method. Okay, and now finally we can see that there's just a little bit of difference in terms of what the true value is, okay, and what RK4 method is, and that's 0.5 dt. Okay, but we're already kind of within 1/1000th of an error, and so based upon what we have for our exit criterion, this might be good enough. Okay, it's very, very accurate, and of course it's fourth order, and therefore globally it's going to be on the order of delta t squared. Okay, sorry, delta t to the fourth, so it's 0.5 to the 4, which is getting to be a relatively small number. In fact, this region about right here. All right, well, let's see, what does it take to kind of get the Hoynes method down to it, and so we're just going to compare Hoynes method at 0.1. Okay, and the RK4 method at 0.1. Okay, and we're actually going to leave, sorry, RK4 method is 0.5, Hoynes method is 0.1, and Euler's method is 0.1. We're going to compare these now to each other. It's running, it's plotting, and I bring it over. Okay, and so again, you can take a look at the values of dt. We're going to zoom in once my mouse turns that on. We'll focus in on it. Okay, and now we can see that Hoynes method at 0.1, right, does a little bit better than the RK4 method at 0.5, but we had to do 5 times more work to make that progress. So I'm going to do one more time with the RK4 method at 0.1, 0.1, and 0.1. We'll see how accurate we can get all these results. I'm going to suppress a lot of these things now that we know what they're producing. All right, those are DTH, DTR. I don't have those suppressed. Okay, and then I've got 0.1 across the board right here. I'm going to click on my zoom in. Whoops, I toggled it off already. Okay, I'll zoom this point. Looks like Euler's method is doing much better, of course at 0.1, but still not as good as Hoynes and RK4. I'm going to start moving in towards this point right here. Okay, and so Hoynes method, there's a slight black line right here, so we know RK4 is doing even better. I'm going to let Hoynes method drop off and just focus on the RK4 method. And I have to go really quite close, okay, in terms of the difference between this blue line, the cyan, and this black line, and we're getting down to 1 part in 10,000 in terms of the differences at this particular time value right here. So RK4 method does a fantastic job of trying to model, okay, this particular exact solution using a numerical method, and we never had to go off and solve the precise integration. Okay, so back to the slides here a little bit more. We can do an RK comparison of the other ones as well, okay, and you'll see other things in terms of if the RK4 method at 0.5 and the Hoynes method 0.5 and Euler's method 0.5, you'll see then that instead of kind of the average of 2 slopes, this first blue line right here is going to be the average of, well, 4 slopes. Okay, some of them are going to be somewhere here at 0.25, some of them at 0.25. We take the average, and therefore we're going to try to hit our target almost exactly in comparison to the exact solution. So in terms of comparing RK4 to the other two methods, we know that at every time step you have to do one Euler function. Okay, Hoynes is at 2 functions, and RK4 you have to calculate 4 different function evaluations. Okay, so therefore RK4 requires more function calls per time step, but it outperforms Euler with 5 times bigger time steps. Okay, so in this particular case, we've got 5 times as many time steps for Euler's, okay, and it's still overestimating the result of this particular example. Okay, the time step is really large for RK4, but it's still doing a better job, Hoynes method, even when Hoynes method actually does twice as many function calls. Okay, so it's very beneficial, okay, to do large time steps and do fewer function calls, especially if your function calls are costly or lengthy. Okay, but there is a trade, of course, because Euler's method can work really well if each one of your function calls is fast. Okay, but you can do, or you have to do one for every single time step. So in terms of summary, okay, if the ODEs are explicit, you're going to require 4 derivative function evaluations per time step. As they're consistent, then your local error for one time step is going to be on the order of delta t to the 5th. And then, of course, globally, the whole process is going to be that 4th order sort of idea, delta t to the 4th. As I mentioned, then there's other ways to kind of use multi-points, okay, to kind of extract out the same sort of thing. And this is similar to kind of, again, the trapezoidal method in comparison to Simpson's 1/3 rule and Simpson's 3/8 rule. Okay, we've been looking at kind of time current and time into the future, but you can actually look at time into the past. So essentially you can kind of do a whole bunch of points, okay, in the past and try to extract out some sort of polynomial. Okay, we talked about linear regression, we talked about interpolating polynomials, so you can kind of use that information to kind of see, well, why don't I start with kind of the slope of that polynomial and move forward in time a little bit and use it, okay, in some sort of average sense to try to extract out what the next sort of slope should be from a next point. Okay, so of course we can use information at the current step right here, but we can also use information at the previous steps to generate that estimate of the slope for the next step. So there's a whole bunch of other methods to kind of do this. There's even adaptive methods where you might take smaller steps or larger steps based upon what you know about the function. If it's very linear, well, then you can take maybe larger steps. If it's highly nonlinear, you need to shorten down those time steps. In addition to kind of the explicit methods that we talk about in ME 273, there's also implicit methods. Okay, so we can actually include slope information at the next time step in terms of trying to figure out, well, if I knew something about the future state, then I could be better at trying to hit that target right now. This, of course, might require that you solve a solution of systems of equations because then you're trying to solve a whole bunch of things that need to match and converge all at the same time. Now, solving a system of ordinary differential equations is very similar to solving just one at a time, except now you have to kind of solve each one of them simultaneously for every time step. Okay, so in this particular case, right? If you recall in the very first part, we talked about how sometimes you have ordinary differential equations that have higher orders. You might need to break them up into two first order ordinary differential equations, and then you can use the methods, whether it's Euler's or Hoynes or RK4, to solve these problems. Okay? When using, of course, these methods, make sure that the intermediate values are computed for all the equations before you move on. Therefore, you can't solve for y1 for all time steps and then solve for all times for the second variable, because then this second equation uses information from the first one. So you have to solve for the first time step both equations, then the next time step both equations, and so on and so forth. So solving systems using Euler's method, well, simply march each equation forward simultaneously, right? You do this one line of code, okay, just in taking an Euler step, extracting out the slope information, and increasing I to I plus 1 for this one, and then using that same information for this one, and then going back and increasing this value to the next time step, and then this value to the next time step, and so on and so forth. Again, you can't do this entire dimension all by itself and then this entire dimension. You have to do both of them together simultaneously. Similar with Hoynes' method then, those two predictor steps have to be done for every time step before you can move on to the next time. As a result, then you're going to do this first equation on the top right here, then this equation, and then you're going to return back, okay, to those predictor steps and then use it again, time and time again. Likewise, then with RK4, you're going to have to do 4 of those slopes all at the same time step, and sometimes at the half time step, instead of just averaging all 2 of them. Like Hoynes' method, you have to average all 4 of those slopes. So how do we do this? Well, we're going to start with the second order ordinary differential equation, right, like this. Okay. You'll notice that it's not with respect to t, it's with respect to x, and so we're going to make those modifications in our program here a little bit. Okay, and then of course, using the approach mentioned earlier, we're going to do a intermediate value of dy dx, okay, and we'll set that to be equal to v, but it's nothing more than a first order ordinary differential equation that we need to solve with this other first order ordinary differential equation at the same time. Okay, and so again, in the same sort of process, we have this slope information is a function of v and y, but we have 2 equations that are then going to satisfy the sort of 2-dimensional slope information from this second order ordinary differential equation. All right, so second order, of course, this is easily solved with Euler's, as we talked about. Okay, we've got these 2 steps right here. Okay, and more specifically, we can replace those functions with the exact sort of calculation of those slopes right here and here. And we'll show this here in MATLAB in just a second. Okay, and then similarly, if you use RK4 or Hoynes' method, which I didn't show, you do these types of calculations right here, all the way down until, of course, you get the next y value and the next v value, and then you've got those 2 dimensions all at the same time being solved simultaneously.